Hello everybody, this is Dr. Hassan again in Power Electronics. We're still in module 2, which is controlled AC-DC and DC-DC converter, and this is week number 6. We are going to discuss Cook and full bridge buck boost and Cook full bridge converter. How this circuit work? You see, when I switch on here, this diode will be open circuit and the current follow through the inductance and store energy. When I open it, the energy released through the diode will conduct, and we have here when the switch here is on, diode is off, and you can see capacitor with the resistance in parallel, and when the switch is off, diode here is on, the energy release here. So the current of the inductance coming from the supply and from the releasing of the energy. If I plot the voltage and current of the inductance and voltage and inductance voltage and current, I will find at the beginning this voltage apply across the inductance, so I have VD, and when we switch off the switch here, this resistance, inductance, capacitance, resistance are in parallel, so we have minus VO, and the current increase, decrease, store, release, and I inductance is the current coming from the supply and current released from the output, as you can see here. I can easily derive formula for them, so I derive formula similar to the discussion for buck and boost separately. V out over Vd equal D, which is for step down, 1 over D, 1 minus D is the step up. In another way, we can find it by just integrating and adding the values. Vd, as you can see here, at T on, which is DTS, and minus VO at T off, which is 1 minus DTS. Just rearrange, we come up with the same formula. As we assume always that input power equal output power, we can use it to find the relationship between input output current with respect to these. Now also we usually discuss the boundary condition. For boundary condition, the same figure has, as you can see here, only the values here changed. So if we follow the same procedure in our discussion, IL boundary equal 1 over 2 IL peak, and when we look from this side, it will be VD here times T on, which is DTS, okay, and ILB we can substitute for VD, because we know that VD is VO 1 minus D over D from the formula we derived before, which is D over 1 minus D. So we can substitute it to come up in term of let me say, so when we substitute, we convert the formula here in terms of VO. Now also we can find IOB since we know that the output current is IL minus ID, and we can look to the output current in this way from this direction, okay, and then we substitute to find it in term of V output. Now here we can sketch both of them, this formula and this formula, okay, IL and IOB. Here we can see that IL is this line, straight line, and the curve here is IOB, okay, IO, and it seems to be, it's not anymore pulse, it's a straight line or a curve in this way. It's peak at 0 D, you can see this is Z. When we have 0 D, 0 here or 0 here, we have the maximum, so we can come up with IOB max, and then we substituted here to and here to find ILB and IOB in terms of maximum L and B currents. For discontinuous conduction mode, we repeat the same discussion. On is the same, DTS or T on. T off will be two parts, delta 1 TS and 0 here, which is delta 2 TS. So we repeat the same discussion. This is from previous slide, and we can find the relationship between output and input voltage is D over delta 1, and since P input equal P output, we can use it to find the relationship between output and input currents, which is the opposite here. And also IL, if we substitute for VO, okay, in term of VO, then become in term of VD, we have this formula, okay. Now I can rearrange, take this part down here okay, and take square root here, and substitute, we simplify using this formula. Okay, we got the relationship for D in terms of continuous conduction mode in this mode. Now if I sketch the previous equation here, this is D, this is IOB over IO over IOB, and this is VD for different values. We can see there is a straight line here, which is the linear, which is the continuous conduction mode, while the curves here, similar to the previous two circuits, is this continuous conduction mode. Now let's example on this. A buck-boost converter operating at 20 kHz, inductance given, output capacitor is sufficiently large, and VD is the dead input voltage is 15 volt. The output voltage is regulated at 10 volt, and the converter is supplying load of 10 watt. Calculate the duty ratio. Now in this question, he didn't tell me that this is continuous or discontinuous. So by default, I assume it is continuous and start with the formula for D, which is D over 1 minus D equal V out over V input. I got D initially 0.4. Then I calculate IOB max. We have formula for it. We just substitute. All these values are given in the question. I got 5 amp. And IOB, in terms of IOB max, we can substitute. We got IO boundary is 1.8. But in the question, he gave me power output and voltage output. I got the current output current. Output current is lower. You can see here 1.8 is the boundary. Boundary is here 1.8. I is 1 amp, is lower. So this means that we are in discontinuous conduction mode. It's discontinuous conduction mode. But I remember for discontinuous conduction mode, I have formula. So I substitute for VO, VD, IO max. I got the actual duty cycle, which is 0.3. As you can see here, it's lower than the initial one. One more issue here is the ripple voltage. Ripple in voltage. It's similar exactly to the boost converter. Okay, here we have charge, here we have discharge. This is the current of the diode. When the switch is on, the zero current, and when the switch is off, the same current of the switch will follow through the, or from the input will follow through the diode. Okay, so if I want to find delta VO, the ripple in voltage is delta Q over C, and I will take this one delta Q. It's rectangular. From here to here is DTS, which is T on, and the height here to here is IO. So I substituted. IO is VO over R. I substituted, and now I can simplify. Take VO here down. It will be delta VO over VO equal DTS. I will assume RC as usual to be tau. Then I have this simple formula to find the ripple in voltage. This is used in many applications. One of them is when we have solar panel or PV array, okay, photovoltaic array. We can use this buck-boost converter to provide the needed power and voltage current to the load, or through battery to inverter, and then we give it to load. This is another way. Okay, you can see here sometimes we use rectifier or engine, okay, then through battery to inverter and then to a load connected by this DC-DC converter buck-boost. Another type of converter which is similar to buck-boost, stepping up, stepping down, but the difference here is we have two inductances L1 and L2 and two capacitances C1 and C2 or C. Okay, the same, we have one switch here as you can see and one diode here. Now this circuit is work in two mode. When the switch is on, inductors connected here to the supply, this diode will be off, current will follow from here through this part. So we have this circuit as you can see here. This is an on and this is an off. Okay, this is an on. When switch is off, current will follow through the diode and this part from here. So we have current following in this direction and current following in this direction. Now if I come to find the voltages of the two inductances and their currents, okay, now for the first inductance at on, this is on, okay, you can see the voltage here applied across the inductance. So we have VD. When it is off, the voltage here is the difference between VD and VC1. As you see, VC1 minus VO. Okay, sorry, here VD minus VC1. The same thing could be say for the second inductance here. When on, this inductance voltage is VO minus VC1, as you can see here, VC1 minus VO. And when we have off, which is here, this one, the voltage of inductance, this one will be in parallel with C and VO, so it will be minus VO. What about current? In on, current charge or energy store, and in off, release. By the way, the difference between this way and the previous way of discussion is I started from off to on, not from on to off. Now, after I explain the operation of the circuit and the waveforms, let me start. I copy here, paste it again, the waveform. I will start with finding formula to relate input to output voltage. First of all, VC1 is VD VO in the on state of the when we're talking about inductance number 1. So I can write formula. I will say, okay, VD by T on equal this voltage VD minus VC by T off. Rearrange, I got this formula. I come to inductance number 2. This voltage by D on, T on, and this voltage by T off. I arrange, I come up with another formula. See, VC1 equal VC1, so this element equal this element. I arrange them, I got the same formula for buck boost converter. Since we usually assume Pin equal P out, okay, I can use it to find the relationship between output to input current, which is the opposite, similar to the previous situation. Now, let's take example on Cook converter. He told me that Cook converter, its frequency is, by the way, before I continue with the example here, just to let you know that we assume usually the capacitor is a large, sufficiently large, and it would have constant voltage, and the current in the inductance is constant current. It means the current is increasing in this way, decreasing in this way, not in this way, decreasing in this way. No curve, just straight line. Okay. Now back to the example. He gave me L1, L2, they are equal 1 millihenry. Capacitor C1 is 5 microfarad. The output capacitor is sufficiently large, yield essential constant voltage. This is my assumption all the time. Now the input voltage is 10, the output voltage is 5, and it is supplying 5 watt. Oh, he told me the output voltage, power also. Calculate the percentage error in assuming constant voltage across the capacitor and constant current across the inductances. Now for the capacitor, we say it's the highest voltage in the circuit, which is input plus output, 15 volt. And I have formula D over 1 minus D equal output over input. I got duty cycle because I need duty cycle. Now let's come to delta IL1. Delta IL1 is, as you know, the voltage over L1 times off time. Okay? Now I have VC, VD, LD, TS. I substituted, I got this current. Let's go to delta IL2. Also, I have the formula output voltage over L2 times T off. I have all these values. Substitute, I got the same current. Since the current is the same, this means that the inductances are the same. Okay. And I can find the error. How? Have a look. This is the current 0.67 over delta IL1 over IL1, which is 0.5. I have it in the question. Then I multiply by 100%, it gives me 13.4%. This is how much the error in assuming delta IL1 constant. The same thing I did with delta IL2 over IL2, 0.67 times 100% over the current IL2, it gives me 6.7. This is the error. This is with respect to current. For voltage, let's see. Delta VC1 is 1 over C integration IL1, because IL1 follow in C1, okay, for off time. And IL1, I have it, 0.5. I just need to substitute here, duty cycle, okay, and here the capacitor, here IL, okay, then I got the voltage. Divide ripple in voltage over voltage VC1, it seems to be there is some sort of error. So this is need to be considered in the real design. Now, last converter, I finished buck boost, and Cook converter. Last one is the DC, is the full bridge DC converter, which may be used to control one of the application is DC motor. You know, this is DC motor, RI, LI, and back EMF. And you can see here we have leg A. This is leg A, contain two switches, TA positive, TA negative, which means that A positive connect to positive side, TA negative to the negative side. The same thing could be said for the other switch, TB positive, TB negative. Okay, for leg B. Now the load is connected here to the center of, to the center here of leg A and to the center of leg B. One more issue need to be mentioned here. For each switch, we usually connect anti-parallel diode, D. It means in parallel but in opposite. I call it as example TDA, DA positive, DA negative, DB positive, DB negative. You may say, okay, why we connect these diodes? First of all, to protect the circuit, protect the switch, and to make a path for the current to follow through in situation the current reverses direction. As example, energy stored in the inductance released, we can use it. Now let me talk about one of these legs, leg A as example. When TA positive, current will follow here, okay? So the voltage here is the voltage VD. So you see here, VAN, between this is A, okay? As you can see here, the middle, A, and this is N, the ground. Then it's equal VD. When this one is positive, this one is 0, is off. When this one is on and TA positive is off, we have 0 current because this point connected directly to the negative. Okay. Now the difference between this point A and this point B will give me the output voltage. As you can see here, V output is VAN minus VBN. It's worth mentioning that the switch can be controlled using bipolar pulse width modulation, bipolar or unipolar. In bipolar technique, we switch off pair of switches. It means TA positive with TBB negative. Current follow from the positive to negative back here. Let me change the color. Okay. When I switch current TB positive, okay, TB positive follow through the switch and return back here, then I have the voltage across the. Now last issue is if I compare the output power with respect to the switch power in term with respect to the x-axis, the D, I can see the step up is a straight line, the step down is straight line, and the pulse here represent the buck boost and the Cook converter, while here is the full bridge. What can I come up from this figure? I come up that there is variety of control, good control for buck boost, Cook converter, and full bridge. Okay, but limitation in the output power. From the other side, better output power, I can go up to 100% for step down and step up, but the variety in control is limited. I will stop here.